This is multivariable calculus. And in multivariable calculus, I think it makes sense to start with what are called parametric curves. And that's what our textbook does as well. Parametric curves are defined by parametric equations. And in 2D, it's a system of two equations. X equals some function of time, call it f of t, and y equals some function of time, call it g of t. And you think of this as a system of equations, as a pair of equations that go together to define a parametric curve. These are parametric equations. T is typically thought of as time, though as the textbook author emphasizes, it doesn't have to be time. And there are some applications where it's not time. Probably the most common other kind of applications, the parameter is an angle, call it theta, say. It's probably the most other kind of common applications of parametric equations, but most commonly, t is time. T is the parameter. It's typically time. I'll put the word time in quotes. Again, it doesn't have to be time. And the units you measure time in are kind of up to you. It depends on the application. Could be hours, could be days, could be minutes, but most typically it's going to be seconds. And f and g are functions. What kind of functions? Well, mostly the kind you always encounter. Could be quadratic functions, t squared plus 5t minus 3 or something, or a cubic, or a general polynomial. But they could be other kinds of functions. Trig functions, cosine and sine are common. They could be exponential functions. That comes up in differential equations, for example. Exponential growth or exponential decay, or maybe one of these is exponential growth and one's exponential decay. There's lots of different functions they could be, but in the abstract, you just want them to be typically continuous and hopefully even also differentiable. Continuous basically meaning that if you graph them individually, you get graphs that don't have any breaks in them, right? No holes in the graph, no asymptotes, no jump discontinuities. Differentiable meaning they have a derivative. They're smooth everywhere, no corners in the graph like the absolute value function. Could they have corners? Could we consider non-differentiable functions? Sure. But for most applications, you want them to be nice and differentiable, having a derivative. There's also something called continuously differentiable, which means not only does the derivative exist, but also the derivative is continuous, which sounds like, well, why wouldn't it be continuous? The answer is because there actually are functions that are differentiable everywhere, but that derivative is not continuous. It's really, really weird. I might show you examples of that later. The parameter is the independent variable. So you got a single independent variable, t, but x and y are both dependent variables. So it's like you've got two dependent variables. However, you can change your perspective on this and think of that those two dependent variables as a single two-dimensional dependent variable. You could effectively combine these, into a quote unquote point x comma y equals f of t comma g of t. And that point becomes a single two-dimensional dependent variable, if you like. Either perspective is okay. Either two dependent variables with two separate functions, f and g, or as a single dependent two-dimensional variable based on a single two-dimensional function, you might say, that has component functions or coordinate functions. This is a single two-dimensional function having is what I'm trying to write here, two component or coordinate functions, f and g. Or we can think of them being combined into a single two-dimensional function. These conceptual ideas that I'm trying to emphasize here are important to understand. It is a point of confusion for many people to not get what I'm saying right here. And it's important. It's going to generalize, for one thing. Should you use the word component or component if you prefer, or coordinate? Either one's okay. If you use the word component, that's a word, well, partially reserved sometimes more for vectors, and partially reserved sometimes more if you are thinking about these just as what are called ordered pairs. Two quantities inside parentheses separated by a comma. You can call them coordinates as well, though that has some hidden connotations. What kind of coordinates? Standard rectangular coordinates? Skewed coordinates where your axes are skewed to not be perpendicular. People who take differential equations and linear algebra learn a lot about that. Polar coordinates. Maybe you know about polar coordinates. They could be polar coordinates. I'm seemingly emphasizing that they are standard rectangular coordinates by calling these x and y. But I could have used r and theta. I could think of these in terms of polar coordinates and graph them in terms of polar coordinates. That is allowed. You have to change how you think about things when you do that, but it is allowed. How you visualize these things is not unique. There are infinitely many ways of visualizing these things, but there's sort of one standard way of doing it with standard rectangular coordinates. The simplest kind of thing to do. Yeah, and as t varies, this is going to trace out a curve. In general, it could be some wild curve going all over the place, maybe even crossing itself, something like that. Why does this happen? You should understand it conceptually. It's because x and y are changing over time. So the point changes, it moves. In fact, the main kind of application we're going to emphasize for these things is motion. This is going to be very useful for your mechanics class, where that's the study of motion. And it's motion that's got a direction to it. Because t increases, right? I mean, we could let t decrease, but usually you want to imagine t increasing. Time is going by. So it's not any old motion along this curve. It's got a certain direction, like the direction I drew it in. So you want to also draw arrows. But there's another subtlety that this drawing can't illustrate. And that subtlety is the motion is not only in this direction, but it could be motion that speeds up and slows down. Goes fast, then slows down, then goes fast again, then slows down, then goes fast again, then slows down, or even turn around and go the other way, which would mean I'd need to draw the arrows going the other way too, and somehow both directions, depending on what t is. That could happen. It could be back and forth motion too. That could happen. Let's take an example. Let's let x equal f of t be t squared minus 1, and y equal g of t be t cubed. Actually, I'm going to do t cubed minus t. First thing we want to understand is how to plot this curve even by hand. So if you're going to do it by hand, which is worthwhile to do, we should make a table. plot points. We need a table for all three variables. Let's put it over here, t, x, and y. Let's pick some values for t. T is the independent variable. Let it take on, say, somewhat standard values like -3, -2, -1. Some interesting things go on here near 0 here. So I'm also going to pick -0.5, 0, +0.5, +1, 2, 3. I am going to be helped in plotting points and filling in numbers in the table by the fact that this is a f is an even function and g is an odd function. And there I am. I forgot to show myself. F is an even function, G is an odd function. Plug in some numbers. First into F. -3 squared is +9, -1 is +8. -2 squared is 4, -1 is +3. -1 squared is +1, and -1 is 0. -0.5 squared is +0.25, -1's -0.75. Plug in 0, get -1. Yeah, f is an even function. The values to the right of 0 are going to match the values to the left of 0. So I'll go back to -0.75 here, 0, 3, and 8. How about g? Plug in -3. -3 cubed is -27. Minus -3 is -24, right? -27 minus -3. -27 plus 3. -24. Plug in -2, get -8 minus -2. -8 plus 2 ultimately is -6. Plug in -1, get -1 minus -1 is 0. Oh, this curve's going to go through the origin, right? 0, 0. Look at the x and y coordinates. Plug in -0.5. Okay, I better use my calculator so I don't make a mistake. -0.5 cubed minus -0.5. Positive 0.375. Plug in t equals 0, get 0. This is an odd function. The value at t equals 0.5 is going to be the opposite of the value at t equals -0.5. 0.5 cubed minus 0.5 is -0.375. At 1, I'll get 0. At 2, I'll get +6. And at 3, I'll get +24. Plot points. The x and y coordinates, not the t coordinate. I will try to make my scale big enough to include all these points. So let's say this is -25 here, +25, +25, -25. I'll try to do it as accurately as I can here. These are 5, 10, 15, 20, 5, 10, 15, 20, -5, -10, -15, -20. Same kind of thing over here. Not perfect, but good enough. First point to plot has x coordinate 8 and y coordinate -24. It's going to be right down here, right about down here. Next, coordinates 3, -6, right about here. Next, 0, 0 goes to the origin. Next, -0.75, +0.375, really close to the origin, slightly closer to the x-axis than the y. It's going to be a tight curve in here, it looks like. -1, 0 is maybe right about here. Then I'd go down here. Then back to the origin again. 3, 6 is right about here. And then 824 is right around here. So the curve seems to be doing something about like this. Connect these dots with a smooth curve, continuous and smooth. It is a nice function. Doing something about like this. In that direction as t increases. So draw some arrows indicating the direction as t increases. That's supposed to be a little arrow there. It's hard to see. We could zoom in near the origin, make it bigger near the origin if we wanted to. We'd see the little loop-the-loop better. So this curve does that kind of thing. That's the motion, seemingly. But is it the motion? There's more going on here than meets the eye. The speed is not constant along the curve. The motion is not a constant speed motion. How can we see it with a calculator? You go to your mode, first of all, and go out of function mode. Go to par or parametric. My calculator looks like this. Then when you go to your y equals screen, it'll look different than usual. Looks like that. X and y depend on t, not y depending on x. Plug in these functions. T squared minus 1 and t cubed minus t. How'd I get the t to show up? I plugged the usual variable button, but instead of an x, it came up as a t. In your window, we are starting t at a negative value. Sometimes you would want to start t at 0. But here we're starting at -3. So I'm going to go from -3 up to 3. The t step effectively tells you how many points to plot. Every 0.1 units of t, 0.01 units of t. Making it bigger makes the curve get traced faster, but less accurately. Making it smaller, the curve gets traced more slowly, more points are being plotted, but it is more accurate. I will do the -25 to 25 here as well for both x and y. Make my tick marks 5 units apart. Graph it, we will see the curve. Now, just watch. I'm about to graph it. Watch the speed change. Ready? 1, 2, 3, go. Slowing down, isn't it? It's going slower near the origin. Seems like it's stopped. Then it's speeding up. So it's not just the curve, it's the speed information too. Fast at first, then it slows down near the origin, then it gets faster again. If I zoom in closer to the origin, we'll see the loop-to-loop better. Here we go. There it is. Okay. So that's our first example of a parametric curve. What can we do with this besides plot points? Lots. One example of something we can do is we can find x and y components of velocities. I can find dx dt and dy dt. X is f of t, so dx dt is f prime of t. Y is g of t, so dy dt is g prime of t. And for this example, f is t squared minus 1, so f prime is 2t. G is t cubed minus t, so g prime is 3t squared minus 1. These are the x and y components, you could call them, of velocity. What is velocity? Velocity is really a vector. We're not going to talk about vectors in chapter 9, but we will starting in chapter 10. For the moment, we can put these things together as a point. We could write it this way. We could write dx dt, comma dy dt as a two-dimensional velocity. Could call it a vector, but I won't at the moment. F prime of t, comma g prime of t. Those are the components of the velocity. They simplify for our example to 2t, comma 3t squared minus 1. Hey, that's a parametric curve too. It could be graphed. Does its graph tell you information about this graph? Just like in ordinary calculus, the graph of the derivative tells you information about the original function. Yes, but it's tricky. And in fact, it's typically going to be best not to graph this. It's typically going to be best in chapter 11 to think of it as a vector, to think of it as an arrow with a certain direction and a certain magnitude, plotted in a certain way. That's going to be much more informative. But if I wanted to find the velocity of this object at any moment in time, I certainly could do so. At t equals -1, for example, what do I get? Plug in -1, t equals -1, I'll get -2, comma 2, it looks like. Right? Plug in -1 into both formulas there. In this graph, at time equals -1, I'm right here. In fact, you can put the t information in the picture, but it's with a label. T equals, -3 here, -2 here. You're at the origin at -1. You're also at the origin at +1 after you go through the loop. You're at this point here when t is -0.5. When t is 0, you're at this point here. T is +0.5. T is back to +1. You're back to the origin. Here you're at that location when t is 2, and here when t is 3. So you can put the t information in the picture, just not as a graph. It's got to be labels. What does the velocity at time -1 mean? The x velocity, the x component being -2, means at that moment in time, your velocity in the x direction is -2. That's the instantaneous velocity in the horizontal direction. And it's to the left because it's negative. And your instantaneous velocity in the vertical direction is +2, upward. Yeah, at this point right here, as we travel this way and come to the origin, we are moving to the northwest. X is decreasing and y is increasing. That's why this derivative is negative and that derivative is positive. Maybe it's useful to figure out where these things are 0. If I set dx dt equal to 0, dx dt is true t, that means true t is 0, that means t is 0. The x component of the velocity is 0 when t is 0. Hey, that's when we are at the leftmost point. The motion's like this. Oops, the other way. Like this. At that leftmost point, the x component of velocity is 0 because your tangent to that curve is vertical. Yeah, in fact, that is where the tangent to the curve is vertical. If I set dy dt equal to 0, dy dt is 3t squared minus 1. That means ultimately t squared is 1/3. So t is plus or minus square root of 1/3. not a nice number. Plus or minus 1 over root 3. Or if you feel like rationalizing the denominator, plus or minus root 3 over 3. By the way, it's not required to rationalize denominators in this class, in spite of what your high school teacher told you. You don't have to rationalize the denominator. It's okay to write it like that. At that moment in time, which is less than 1, it's between 0 and 1, plus or minus. That's where dy dt is 0, where the vertical component of velocity is 0. That's where the tangent is horizontal. Close to negative 0.5 and positive 0.5. I bet it's not exactly those, right? Because this is not plus or minus 0.5. About plus or minus 0.58 is where the tangent is horizontal. Close to plus or minus 0.5. So I can figure out where the tangent is vertical and horizontal. How about any slope? This is the last thing we'll do today. How about any slope? Use this equation. dy dx, the slope is dy dt divided by dx dt, which for this example, so that in general is g prime of t divided by f prime of t, which for this example is 3t squared minus 1 over 2t. So for any moment in time, you can find the slope. Now this is a little weird. dy dx is a function of t? Yeah, you can simplify it to a function of t is what that's telling you. Could you find it as a function of x? Maybe, but we don't need to. It's good enough to have it as a function of t to find the slope of the curve at any moment in time. If you've got a moment in time like t equals -1, you can plug that in here and find the slope. I'll go ahead and do that. dy dx when t is -1 is going to be what? 2 over -2 is -1. That means the slope of the curve at the point 0, 0 when t is -1 is -1. The tangent to the curve at that point is -1. But wait a minute, the curve crosses itself. Isn't the slope also something else? Yeah. When t is +1, when you come back around and come to the same point, the slope becomes +1. So at that point, there are really two slopes, depending on whether you're at t equals -1 or t equals +1. Where does this equation come from? It can be derived from the chain rule, but we don't have time today.